Welcome back. In the second half of this lecture, we're now going to talk about how we'd find algebraically the function inverse. So we've talked about how you'd find the graph of a function's inverse, and we did that just by switching x's and y's. Anything that was an x property became a y property for f inverse, and anything that was a y property for f became an x property for f inverse. Any x and y points, we switch those coordinates to become y and x. So in other words, we were just switching x's and y's in all senses. And that actually is kind of what's going to go on here when we're finding the inverse of our function. So here you have got a function f of x, and it happens to be 1-to-1, which means you know that f inverse will exist. So the plan is, the first step, you just rewrite it as y equals. So if your function was originally x cubed plus 2, then you'd first start off by rewriting it as y equals x cubed plus 2. Because we'd like to see in our definition here y's and x's together, not x's and f of x's. And then the next move would be to switch x's with y's. So just like we said in the graphing thing, anything that's an x becomes a y, and anything that's a y becomes an x. Same thing here, we would then switch the x's with y's, and switch the y's with x's. And then the last thing to do is now take this equation, now that you've switched x's and y's, and solve for y. And whatever y equals to, well, that will be your f inverse. So if you were solving for y, once you've solved for y, now what you found here, that is f inverse. So if your function was x cubed plus 2, then f inverse is cube root of x minus 2. Okay, so we're going to do a couple of examples of this where we're going to find the inverse of a function. And so it's always the same process, always the same procedure. We start off by writing our function as y equals. We switch the x's and the y's. Then we solve for y. And once we've solved for y, there we go. We've found our inverse. So first off, before I find the inverse of this function, if you were to think about, does this function even have an inverse? The answer is yes, it should, because if you're thinking about what is this the graph of, this is the graph of a cubing function that's been shifted 1 to the right. It's been stretched vertically by a factor of 3. It's been shifted down by 2. So really all we're doing is taking a cubic graph and shifting it around and stretching it, and that's about that. It's going to stay as a one-to-one function because it started out as a one-to-one function. If you have something that passes the horizontal line test, you can move it to the left, you can move it to the right, you can stretch it, you can move it up or down, but it will still pass the horizontal line test, which means it will stay as a one-to-one function, which means that for this, for f of x, we know that f inverse should exist. So we'll start off by writing this as y equals. And then the next thing that we'll do is we will switch the x's and the y's. So instead of x equals, instead of y equals, we'll have x equals. Instead of 3 times x minus 1, it'll be 3 times y minus 1. So any x's become y's, any y's become x's, and now all we need to do is solve for y. So now we'll do that. I'll bring the 2 to the other side. I'll divide everybody by 3. I'll take cube root of both sides of the equation. I'll bring the 1 to the other side. And now, at this point, now that we've solved for y, what we have here, that would be f inverse. So I can say f inverse of x should be cube root of x plus 2 over 3 plus 1. And of course, for this, you can check. You can check to see if you have your right answer. You can check to see, does f composed with f inverse, does that equal to x? Does f inverse composed with f, is that equal to x? And if it's true for both, if you say yes to both, well, then you've confirmed that these two things are inverses. So this would be a point where you could pause and check to see that if you take f and compose it with this f inverse, do we get x as our answer? If we have f inverse and we compose it with f, do we get x as our answer? And I can confirm that yes, these are inverses of each other, but you should do that as an exercise just to see that it works. Also, that means that anytime you're checking to see if one function is an inverse of another, you should be able to check to see if that's true by checking to see the composition of these two functions. If you have a function of f and you think you found f inverse, then you can confirm if your answer's right just by checking these two conditions. If they both hold, then yes, you did find the inverse correctly, and if they don't, then that means you might have missed something. Go back and check your work. And now for this function, g of x, which we haven't graphed something like this yet. We will when we get into chapter 5, so very soon. But this is a function that would look a little something like this. It has a horizontal asymptote and a vertical asymptote, and it definitely is a one-to-one function. Any horizontal line passes through that graph in exactly one place. It never crosses through in more than one place. So this is a function that should be invertible. G of x should have an inverse. So now let's do that. Let's start off with finding our inverse by writing out y equals our function. And then we'll switch x and y. So we'd have x equals y minus 1 over y plus 2. And then the next thing that we need to do is solve for y. So what I'll do now is I'm going to take this y plus 2 that I have in the denominator, and I'm going to bring that up. So I'd have x times y plus 2 equals y minus 1. I'm just going to expand out what I have on the left side. And I'm going to bring, since I want to solve for y, I'll bring everybody with a y to one side, and I'll bring everybody else to the other. And I'll factor out the y on the left side. And now I can solve for y by dividing everyone by x minus 1. And if we want to make this look a little bit nicer, I could take what I have on the right side and multiply everybody top and bottom by -1, just so that there's not quite so many negatives lying around. There we go, and I've got now solved for y. Y equals 1 plus 2x over 1 minus x. And so you can say now that g inverse should be this function. And the same thing that I said about the previous example is true here as well, that you should be able to check your answers by checking to see if you compose g inverse with g, do you get x as your answer? If you compose g with g inverse, do you get x as your answer? And if the answer is true for both of them, that yes, you get x as your answer, then good, you have found the inverse. That's the nice thing about finding the inverse of a function. It's one of the many things in this course where we can check our answers to see and confirm that we're correct. So the thing that I'd mentioned before, which was that for the graph of f of x versus the graph of f inverse that everything is switched, and that includes domain and range. The domain of f is the range of f inverse, the range of f is the domain of f inverse. And that actually gives us a little bit of a nice thing to work with here. If you're interested in finding the domain and range of f of x, the domain is usually easy enough to find, because for finding the domain, we would just have to ask ourselves which values of x can we put in. And for this one, it's pretty clear what the domain would be. You can put anything except for that excluded value of x being 2. So I'll just write this out now. I'll say that my domain is the set of all x's such that x is not 2. Now, when it comes to the range, that's a little bit less easy to tell, because remember, the range is all the y values that would actually be on the graph of that function of f of x. And unless you know what the graph looks like, it may not be obvious what the range should be. But here's the idea that we'll use, that if you want to find the range of f of x, that's the same thing as the domain of f inverse. So my plan here is, now that I want to find the range of f of x, I'll instead find f inverse and find its domain, because domains are easier to find than ranges. And then once I know the domain of f inverse, then I'll say, well, the range of f of x has to be the same thing. So let's do that. I'm going to now find f inverse. And remember, I do that by first writing out my function as y equals. I switch x and y. So I would have x equals 5 over y minus 2 plus 3. And now I just need to solve for y. And I'll solve for y first by bringing the 3 over to the other side. Okay, so now that I've done that, now that I've brought the 3 over to the other side, I've now got x minus 3 equals 5 over y minus 2. I'll now bring that y minus 2 up to the other side. I'll divide by x minus 3. And I'll bring the 2 over to the other side. And there we go. We can say that f inverse should be 5 over x minus 3 plus 2. And the domain of f inverse is not hard to find. So the domain of f inverse would be any of the values of x that we can put in validly into that function. And you could put anything in except for the excluded value of 3. So I would say my domain for f inverse would be everything except for 3. And now this is the idea again, that we found the domain of f inverse, and that when we find the domain of f inverse, that is the same thing as the range of f of x. So we can say here that since the domain of f inverse is everything except for 3, then that means the range of f, the original function, should be everything except for 3. Remember that the range is y values, so when I say the range of f of x, it would be all the y values such that the y values are not 3. But anybody who's not in the domain of f inverse would be somebody who's not in the range of f. because the range of f is the same thing as the domain of f inverse. We're switching inputs and outputs. We're switching x's with y's. We're switching domains with ranges. So now we have our answer. We have that the domain of f, we found just by looking at it, the domain was everything except for 2, and that the range of f was everything except for 3.